Welcome to Talk Tensors. Today we are looking at a world without crisp lines.
A very blurry world, yeah.
Right. You know, usually when we talk about a diagnostic system, whether that's in medicine or, structural engineering, there is this expectation of absolute binary precision.
Exactly. You want a clear answer.
Yeah, like an X-ray shows a fractured bone as a stark, jagged white line.
Yeah.
Or a stress test on a steel beam shows a definitive fracture point. The diagnostic landscape is categorized with absolute certainty.
But if you step back into the world of early deep learning...
Oh yeah, it's a mess.
And specifically computer vision, back in that era where neural networks were first trying to find the exact physical boundaries of an object in a photograph, that diagnostic certainty just completely vanishes.
Totally. Those early networks didn't see crisp lines at all. They saw these glowing, ambiguous, murky clouds of probability.
It was the absolute definition of diagnostic muddy waters. I mean, the field had built these incredibly powerful engines for image classification, but when you ask those exact same engines to just draw a line around the object they just identified, they failed spectacularly.
The spatial understanding was completely fractured. Which brings us to our mission for this deep dive. Today, we are exploring a classic, truly seminal computer science paper that revolutionized how machines see and understand boundaries in images.
A really foundational piece of work.
It really is. The paper is titled DeepLab, Semantic Image Segmentation with Deep Convolutional Nets, Atrous Convolution, and Fully Connected CRFs. It's authored by Lang, Chu Chen, George Papandreou, Isonis Kokinos, Kevin Murphy, and Alan L. Yu. And if you are following along with your own stack of sources, the link to the original paper is right there in the description for you.
It remains a powerhouse of a paper, even today. I mean, if you've ever used a smartphone camera that seamlessly blurs the background.
Oh, like portrait mode?
Exactly, portrait mode, where it keeps every single stray hair on your subject in perfect, razor-sharp focus, you are interacting with the direct legacy of the architecture described in this work.
That's crazy to think about.
Yeah, they took a problem that was bottlenecking the entire computer vision industry at the time and dismantled it with just incredible mathematical elegance.
So to really grasp why this paper hit the community like a thunderbolt, we have to establish the tension, the fundamental friction between two distinct tasks, image classification and semantic image segmentation.
Right. They sound similar, but they are essentially at war with each other.
Exactly. And since you, our listeners, are already deeply familiar with the mechanics of deep learning, we don't need to retread the basics of, what a convolutional layer is, but we do need to look at how the optimization goals of classification actively sabotage the goals of segmentation.
That is the core conflict right there. Image classification demands that an algorithm looks at an array of pixels and collapses all that high-dimensional data into a single probability distribution.
It just wants one word: dog.
Exactly. It assigns one label to the entire image. And to do that effectively, the network must develop a really high degree of spatial invariance.
Meaning it doesn't care where the object is.
Right. If a motorcycle is in the top left corner, the bottom right corner, if it's scaled down, or if it's partially occluded behind a tree, the network still needs to output the label motorcycle.
So the network is actively rewarded for throwing away spatial information.
Yes.
Abstraction is the ultimate goal. You are forcing the model to ignore the where so it can confidently output the what.
And it does this through successive layers of spatial decimation, striding and pooling operations that drastically shrink the feature maps as you move deeper into the network.
But semantic image segmentation requires the exact opposite.
That's a totally different ballgame.
You aren't just summarizing an image into a single semantic concept. You are forced to map that semantic meaning back onto the high-resolution physical space of the original photograph. I mean, every single pixel in a 2-megapixel image requires its own discrete class label.
You need the high-level semantic abstraction to know it's a motorcycle in the first place, but
you need the low-level spatial fidelity to know exactly which pixel is the chrome exhaust pipe and which pixel is the gray asphalt beneath it.
It's a massive paradox.
It really is. And the basis for why we are spending this entire deep dive on the DeepLab paper is how brilliantly they resolve this paradox. They prove that you don't need highly complex, fragile, multi-stage cascading pipelines to recover those lost object boundaries.
They completely bypass the brute force methods of the time.
Right. They explicitly controlled the resolution of the neural network with a borrowed mathematical technique called Atrous Convolution, which we'll get into.
Oh, we will definitely get into that.
They captured the scale of highly varied objects using parallel spatial pyramid pooling, and they snapped their blurry abstract predictions to perfect pixel-accurate edges using probabilistic graphical models, specifically fully connected conditional random fields.
It was just a masterful synthesis. I mean, they took separate, deeply complex mathematical concepts, some originating from the signal processing of the 1980s, others from the statistical mechanics used in physics.
Wait, physics?
Yeah, the CRFs have roots in statistical mechanics, and they fused them all into an end-to-end adaptable system that absolutely shattered the state-of-the-art benchmarks on datasets like Pascal VOC.
So we're going to get incredibly technical today. We're going to dive into the architecture, the specific mechanics of the mathematical optimization, the hardware constraints of the era, and the historical context. We're going to break down the exact mechanisms that allowed DeepLab to see the world so clearly.
And to set that historical context properly, we really need to rewind to the era just before this paper was published. We are looking at the landscape around 2014 and early 2015.
Okay, let's set the stage. Deep convolutional neural networks, the DCNNs, were absolute rock stars at that moment.
Oh, they were everywhere.
Architectures like VGG16 and the emerging ResNet models were completely dominating the ImageNet benchmarks.
The field was euphoric. I mean, AlexNet had broken the dam back in 2012, and by 2014, researchers realized that by stacking many smaller convolutional filters and pushing the networks deeper, they could learn incredibly rich hierarchical representations of visual data.
We finally had machines that could reliably extract features from wild, varied, unconstrained data sets.
Exactly. But that massive success in classification created a huge blind spot for dense prediction tasks.
What we call the localization dilemma. The Achilles heel of these deep networks was that built-in translation invariance we just talked about. I mean, we all know VGG16 relies on heavy spatial decimation. You stride and pull your way down to extract those deep semantic truths. But let's look at the mechanical math of that decimation. You have an input image, and it passes through a series of max pooling layers.
Right. So in a typical architecture like VGG16, you have 5 distinct max pooling operations.
Yep.
And each of those operations halves the spatial dimensions of the feature map. So you are downsampling by a factor of 2, 5 times in a row.
So 2 to the power of 5 is 32.
Exactly. That means your final feature map, the layer that actually holds the deep semantic understanding of the object, has been reduced by a factor of 32 across both the height and the width.
Wow. So if you feed the network a standard, relatively small, 800 by 800 pixel photograph, by the time the data reaches the final classification layer, that image has been crunched down to a tiny 25 by 25 grid of features.
It's essentially a postage stamp. And trying to draw a precise, mathematically rigorous boundary around a complex object like, say, the spokes of a bicycle wheel or the thin legs of a chair using a 25 by 25 grid is effectively impossible.
Right.
It is like trying to paint a highly detailed miniature portrait using a massive, heavy-duty house painting brush. The resolution simply does not exist in the data structure anymore.
And the visual result of this is that blobby heat map effect. The authors include a really fantastic visual in the paper of an airplane from the Pascal dataset.
Yeah, that image really sells the problem.
It does. The DCNN clearly activates around the airplane. The network is screaming, "There is an airplane here." But the output prediction is just this amorphous, glowing red cloud, roughly in the shape of a fuselage. I mean, the wings bleed into the sky, the tail fin is completely lost, the sharp physical edges are entirely obliterated by the pooling operations.
The spatial abstraction gives you the conceptual what, but it completely destroys the physical where. And the computer vision community in 2014 was agonizing over how to reconstruct that lost spatial data.
Which leads us to the competing approaches of the time. Before DeepLab introduced its elegant solution, how were researchers trying to put the glasses back in focus? Because the literature from that period is full of incredibly convoluted pipelines.
Yeah, it was a bit of the Wild West. There were 2 main schools of thought, and honestly, both were highly flawed. The first approach was bottom-up segmentation.
Okay, how did that work?
Researchers would use older, traditional, non-deep learning algorithms to chop the original high-resolution image up into what they called superpixels.
Ah, superpixels. Those are basically clusters of adjacent pixels that share similar low-level properties, right? Like similar colors or textures.
Correct. The algorithm groups them together into distinct puzzle pieces based purely on local contrast. Then the researchers would feed each of those individual, oddly shaped superpixel chunks into a DCNN to classify them.
That seems, well, that creates a massive cascading failure risk, doesn't it? If your initial superpixel algorithm makes a mistake, Let's say it groups the brown fur of a dog's tail with the brown dirt on the ground right next to it. The DCNN downstream has absolutely no way to fix that error.
None at all.
It's being fed fundamentally broken puzzle pieces. It's committed to a premature decision made by a much weaker algorithm.
Exactly. It was highly brittle. Now, the second family of approaches tried to solve it entirely within the deep learning framework using deconvolutional networks or encoder-decoder architectures.
Right, I've seen these.
They would let the standard network shrink the image down to that tiny 25 by 25 grid to get the semantic classification. But then they would bolt on entirely new layers to the back of the network whose sole job was to artificially upscale that grid back to the original resolution.
So they forced the network to learn how to unpool the data.
Yes.
But the paper points out that this required massive amounts of extra memory and computing time. You are basically building a massive second network just to undo the structural damage done by the first network.
Exactly.
And we have to remember the hardware constraints of 2014. We aren't dealing with modern clusters of H100s here.
Oh, not even close. We are talking about researchers running these models on single NVIDIA Titan X GPUs with, 12 gigabytes of VRAM?
Yeah, 12 gigs was a luxury back then.
Right. Memory bandwidth was a brutal bottleneck. Stacking massive deconvolutional layers to upscale a feature map by a factor of 32 meant your memory footprint just exploded. You could barely fit a batch size of 1 or 2 into memory, which makes training incredibly unstable and slow. It was a brute force solution to a structural problem.
Let me introduce an analogy here for you, the listener, to really clarify this. So the early DCNNs are basically like looking through a pair of glasses that perfectly identify what you're looking at, like that's a motorcycle. But they blur your vision so badly, you couldn't trace its outline if you tried.
That is a perfect way to put it.
And the researchers were either trying to pre-cut the image before putting the glasses on, or they were taping a second, highly complex pair of magnifying glasses to the back of their heads to try and undo the blur.
Exactly. The spatial abstraction is great for knowing what an object is, but it's totally fatal for knowing where it ends.
And that is the exact friction point where the DeepLab authors step in with their first massive breakthrough. They looked at that factor of 32 reduction and asked a beautifully simple question. What if we just stop downsampling?
It sounds almost painfully obvious in retrospect. If the downsampling is destroying the spatial resolution, just remove the downsampling.
But it's not that simple mechanically, is it? I mean, if you remove the striding from the pooling layers, you keep your high resolution, but your computational cost skyrockets because the network is now doing dense matrix multiplications on massive feature maps in the deep layers.
Right.
And more importantly, you destroy the receptive field of your filters.
That is the crucial second half of the problem. A neural network filter in the deeper layers, let's say a standard 3x3 filter looking for a complex concept like a human face, relies on the fact that the image has been shrunk.
Because the image is small, that 3x3 filter can see the entire face at once.
Exactly. If you stop shrinking the image, that exact same 3x3 filter is suddenly only looking at a tiny patch of skin on the cheek. Its field of view is completely crippled. It can no longer see the big picture.
So to solve this without adding millions of new parameters or completely melting their GPUs, the authors introduced the first major pillar of the paper's methodology, Atrous Convolution.
It is the defining mechanism of the entire architecture.
It is the holy grail of this paper.
Yeah.
And I want to spend a significant amount of time breaking down the actual mechanics of this because it is brilliant. The term atrous comes from the French phrase algorithme atrous, which literally translates to algorithm with holes.
Judge for with holes, yeah.
But this wasn't invented in a vacuum for deep learning, was it?
Not at all. It has a long, rich history in the signal processing community. It was originally developed back in the 1980s and 90s for computing undecimated wavelet transforms.
Okay, unpack that a bit.
Sure. In classical signal processing, if you wanted to analyze a signal at multiple frequency scales using wavelets, you typically decimated or downsampled the signal at each step, much like a max pooling layer in a neural net.
Right.
But if you needed to maintain the exact alignment of your signal over time, decimation ruined your phase data. The algorithm true was developed to expand the wavelet filter itself by inserting zeros between the filter coefficients. This allowed you to analyze broader scales without ever downsampling the underlying data.
So the DeepLab authors pulled this decades-old signal processing trick out of the literature and transplanted it directly into the convolutional layers of a deep neural network. Now, we aren't going to read literal mathematical equations over audio, but let's walk you through the math in plain language. Let's look at how this works in a 1D or 2D spatial domain.
Imagine standard convolution first. You have your filter, a standard 3x3 grid of learned weights. You slide this 3x3 grid over your input feature map. At every step, the filter looks at 9 pixels that are tightly clustered together, all touching each other in a solid square.
Okay.
It multiplies those pixel values by its weights, sums them up, and outputs a single value. In the math, this is an operation with a rate parameter of 1.
The filter is a solid, unbroken block. But in a sorted convolution, you change that rate parameter, right? Let's say you change the rate to 2. You take that exact same 3x3 filter with the exact same 9 learned weights, but you physically spread them out.
Yes.
You insert a blank space, a 0, a hole, between every single active weight in both the horizontal and vertical directions.
And the mathematical beauty here is that you are still only performing 9 multiplication operations. The computational cost, the sheer number of FOPS required, has not changed by a single decimal point.
You haven't added any new parameters for the network to learn.
None. But physically, geometrically, that filter is now spanning a 5x5 area of the input feature map instead of a 3x3 area. It is skipping pixels.
So if you push that rate parameter up to 4, that same tiny 3x3 filter is now spanning a 9x9 area, gathering spatial context from a massive swath of the image, while still only doing 9 basic calculations. I like to visualize this using a physical analogy.
Let's hear it.
Standard convolution is like looking through a thick, solid 3-inch window made of glass. You can see the details directly on the other side with intense clarity, but your view is incredibly narrow. You only see what is right in front of the glass.
Right, it's a very localized, myopic view.
But a Atrous convolution is like looking through a chain link fence instead of a solid window. You are taking your points of observation and spreading them further apart. You can now see the entire yard. You can perceive the broad context of the whole scene without actually needing to manufacture, mount, or look through more actual glass. You achieve a massive field of view using sparse sampling.
That's a really great visualization, and the technical advantage this yields for semantic segmentation cannot be overstated. By implementing a Atrous convolution in the deeper layers of the network, DeepLab was able to completely remove that catastrophic 32x downsampling. They modified the VGG16 network so that it only downsampled the image by a factor of 8.
So an 800 by 800 image now only shrinks down to a 100 by 100 feature map instead of a useless 25 by 25 grid. The spatial resolution is retained.
Exactly.
And because they used a Atrous convolution with a rate of 4 in those final layers, the filters still maintained the exact same massive receptive field they would have had if the image had been shrunk to 25 by 25. The network can still see the big picture, but it sees it on a high-resolution canvas.
But, an 8x reduction is still a reduction. A 100 by 100 feature map is not a pixel-perfect match for an 800 by 800 input image. We still need to get back to the absolute original size for the final evaluation.
And this is where the elegance of their pipeline really shines. Because their feature maps at the 8x reduction level were still so incredibly dense and rich in spatial information, they discovered they didn't need those massive memory-hogging deconvolutional networks to scale it back up.
Right. They bypassed the need to learn an upscaling function entirely. They simply used fast, mathematically basic bilinear interpolation.
But linear interpolation is effectively just mathematical guesswork, right? You have 2 known data points on a grid, and you draw a straight geometric line between them to estimate what the missing values in the middle should be. It's incredibly cheap to compute.
It requires almost zero overhead. Because the class score maps, the raw probabilities output by the network indicating that a pixel belongs to a certain class, are inherently smooth at that 8x scale. Simple bilinear interpolation is more than sufficient to resize a map back to the original full image resolution without losing any semantic fidelity.
And we should emphasize the speed metric here, the practical result of doing it this way. By avoiding complex upscaling layers and using a Atrous convolution, they kept the memory footprint tiny and the computation lightning fast.
Oh, absolutely.
The paper notes that their dense DCNN could operate at 8 frames per second on a single NVIDIA Titan X GPU.
Which is huge. For dense pixel prediction in 2014, achieving 8 FPS with that level of accuracy was blazing fast. It proved that dense prediction didn't have to be a sluggish, memory-bound nightmare.
So we've solved the resolution drop. We maintained a tight 8x spatial grid and used the Atrous filters to keep the field of view wide. But that introduces a secondary problem. Images in the real world are entirely unconstrained, and that brings us to the second major challenge the paper addresses. Objects at multiple scales.
Right.
I mean, you might have an image from the Pascal dataset where a massive cow takes up 80% of the entire foreground frame. But in the exact same image, there might be a tiny dog way off in the background taking up maybe 2% of the pixels. How does the network handle drastically different sizes?
Well, a neural network filter that is perfectly sized and tuned to recognize the specific curvature of the dog's ear will completely fail to recognize the cow because the cow is so massive that the filter just sees an infinite flat wall of brown texture.
The network needs to be scale invariant, but physical convolution filters are inherently fixed in their size. The standard brute force method to solve this at the time was to use an image pyramid, right?
Yes. You take the original high-resolution image and you run it through your massive, deep neural network. Then you artificially shrink the input image by 50% and you run the entire heavy network again. Then you shrink it again and run it a third time. Finally, you aggregate the score maps from all the different runs.
It's effective, I guess, because the network gets to see the cow when it shrunk down to the size of a dog. But from a compute perspective, it is absolutely punishing. You are literally multiplying your processing time by the number of scales you want to analyze. If you want to analyze 4 scales, your 8 FPS pipeline just dropped to 2 FPS. It's a computational sledgehammer.
The DeepLab authors recognized that this was completely unsustainable. They needed a scalpel. And they found their inspiration in a technique called spatial pyramid pooling, which had been utilized heavily in the RCNN architectures for object detection.
So they adapted that concept, merged it with their new favorite tool, and created the second major methodology of the paper, Atrous Spatial Pyramid Pooling, or ASPP. Let's break down how this architecture works mechanically, because it completely eliminates the need to run the whole image multiple times.
Instead of resampling the raw input image over and over, they decided to resample the deep features at multiple scales simultaneously. So the image passes through the bulk of the VGG16 network exactly once. When it reaches the very top of the network, the layer rich with deep semantic features, the architecture branches out.
It creates parallel processing streams.
Exactly. They probe that single incoming high-level feature map with 4 parallel Atrous convolutional layers. All 4 branches use a standard 3x3 filter. But branch 1 uses an Atrous rate of 6. Branch 2 uses a rate of 12. Branch 3 uses a rate of 18. And branch 4 uses a massive rate of 24.
Okay, let's visualize what those branches are actually doing. Branch 1, with a rate of 6, is looking at a relatively tight, localized area of the feature map. It's hunting for the small details, the fine textures. It's perfectly tuned to find the tiny dog in the background.
Right.
Branch 2 and 3 are casting a wider net, looking for mid-sized objects. And branch 4, with a rate of 24, has its filter weights spread so far apart that it is pulling in massive, scrawling contextual information from across the entire image. You can see the giant cow in the foreground, and you can see the sky and the grass around it.
And this is why it's so elegant. Because these 4 branches are running in parallel on a feature map that has already been computed, the computational overhead is a fraction of what an image pyramid requires.
Yeah, that makes sense.
The network simultaneously probes the exact same data for small objects, medium objects, large objects, and global context. It maps them in parallel. It then fuses all of those diverse parallel insights together to make a final scale-aware prediction.
It is an incredibly elegant, computationally cheap solution to the scale problem. So at this point in the architecture, we have high resolution thanks to the 8x limit, we have a massive field of view thanks to the base Atrous convolution, and we have scale invariance thanks to ASPP. The network can see the tiny dog, it can see the giant cow, and it knows exactly where they roughly are in the high resolution grid.
Roughly being the key word there.
Exactly. We still have a problem. Even with Atrous convolution and ASPP, DCNNs are inherently object-centric and spatially invariant. The score maps are still a bit too smooth. The network might say, I am 99% confident this general blob of pixels is a bicycle, but the edges of that blob are soft. They bleed into the background pixels.
Right, it's fuzzy.
How do we get those razor-sharp, pixel-perfect edges that wrap precisely around the thin metal spokes of the tire? And this brings us to the third challenge, which is where the DeepLab paper truly pulls off a magic trick.
The challenge of final localization accuracy. To solve this, the authors realized they had reached the limits of what a convolutional neural network could do on its own. They stepped entirely outside the realm of deep learning and borrowed a heavy-duty mathematical tool from the world of probabilistic graphical models.
The Conditional Random Field.
Yes.
The CRF.
Now, we need to be careful here because historically, CRFs were used quite often in computer vision. But the way earlier researchers used them was fundamentally different from what DeepLab did, right?
Very different. Historically, researchers used short-range CRFs to clean up noisy data. Imagine an older, much weaker semantic segmentation algorithm. It analyzes an image of the sky, but it makes a lot of localized mistakes. It leaves random, isolated pixels classified as bird or building floating in the middle of the blue sky.
It looks like visual static. Exactly. A short-range CRF couples neighboring pixels together, just the pixels immediately touching each other, and essentially applies a smoothing function. It says, if the 4 pixels surrounding you are classified as psi, statistically, you should probably be sky too. It acts as a local smoothing filter to erase the static.
But wait, if we look at the output of our DeepLab DCNN, it doesn't look like static. The neural network's predictions are already too smooth. The edges are already bleeding. If you applied a traditional short-range CRF to the DeepLab output, wouldn't it just act like a blur tool and make the edges even worse?
Oh, it would be actively detrimental. A short-range CRF would take the already soft boundary between the bicycle tire and the road and blur it further. The authors knew this, so they discarded the short-range model entirely. Instead, they adopted a fully connected pairwise CRF.
And fully connected, in this context, is a terrifying phrase computationally. What does that actually mean for the image graph?
It means that every single pixel in the high-resolution photograph is treated as an individual node in a massive, comprehensive mathematical graph.
Wait, every single pixel?
Every single one, and every single node is mathematically connected to every other node in the entire image. The top left corner pixel of the sky is mathematically weighing its relationship against the bottom right corner pixel of the grass.
Let's put a number on that.
Yeah.
If you're processing a standard image with 1 million pixels and every pixel connects to every other pixel, you are looking at a trillion mathematical connections, a trillion edges in your graph.
It was a massive computational hurdle, which is exactly why earlier computer vision methods avoided fully connected CRFs entirely. They were deemed practically impossible to run efficiently.
But we will detail how the authors solved that computational speed issue in a moment. First, we need to look at what this fully connected CRF is actually calculating across all those connections. It operates using an energy function represented as EF. Walk us through the equation. Some thetas plus some thetas. It acts like a strict mathematical accountant balancing a ledger. It calculates a penalty score, and the goal of the algorithm is to minimize that penalty. On one side of the ledger, you have the unary potential, the theta's I.
The unary potential is straightforward. It is simply the baseline guess provided by our deep neural network. It's the log probability guess. The network is essentially saying, based on all my deep spatial features and ASPP branches, I am 90% sure this pixel is a dog. That is a baseline truth the CRF starts with.
It's the network's rough draft. But then you have the second half of the ledger, the pairwise potential, the theta IAG. This is where the magic boundary recovery happens.
The pairwise potential is the penalty system. It evaluates every single pair of pixels in the image pixel A and pixel B and decides whether they should be allowed to have different semantic labels or if they should be forced to share the same label. And it makes this heavily weighted decision using 2 distinct Gaussian kernels.
Let's break down exactly what those kernels are looking at, because they are the secret sauce of the whole paper.
The primary kernel is called the bilateral kernel. It looks at 2 things simultaneously: the physical distance between pixel A and pixel B in the image, and crucially, the actual RGB color difference between them in the original raw high-resolution photograph.
The actual hex code colors of the raw photograph. The CRF goes all the way back to the raw data.
Yes. It anchors the deep semantic abstract prediction to the raw visual reality. This bilateral kernel enforces a strict rule. If 2 pixels are physically close to each other and they have nearly identical RGB color values, the CRF applies a massive mathematical penalty if the network tries to assign them different labels. If you have a cluster of dark brown pixels that make up the edge of a dog's leg and they are right next to each other, the CRF will force them all to be classified as dog.
That makes total sense. And the second kernel?
The second kernel is simpler. It only looks at spatial proximity to enforce smoothness. It penalizes the model for making abrupt, erratic label changes in a very small physical area, regardless of the underlying color. It prevents microfracturing of the labels.
You know, the analogy I use to visualize this interaction is a child's coloring book.
Okay, I like coloring books.
The deep convolutional neural network, with its 8x downsampling and its smooth receptive fields, is like a toddler with a thick crayon. The toddler understands the semantic meaning of the page. They know the dog in the center should be colored brown. But they are messy. They loosely scribble the brown crayon over the dog, coloring outside the lines, bleeding onto the grass. That messy scribble is the unary potential.
Right, it has the what roughly in the right.
Exactly. But the CRF, specifically the pairwise potential using that bilateral kernel, is the sharp, thin, black ink line of the coloring book drawing. The CRF doesn't know what a dog is. It just looks the natural, high-contrast visual edges in the raw photograph's RGB colors, the sudden shift from the brown pixels of the fur to the green pixels of the grass. And it mathematically snaps the toddler's messy brown scribble perfectly to the physical edges of the object.
It is a brilliant symbiosis. The deep neural network provides the high-level semantic meaning, and the statistical CRF provides the microscopic localization by anchoring that meaning to the low-level visual reality of the pixels. It perfectly bridges the gap between deep abstraction and sharp physical detail.
But that brings us back to the trillion connection problem. How do you run a fully connected graph of 1,000,000 pixels, analyzing RGB values and spatial distances across a trillion edges without completely freezing your workstation?
They couldn't compute it brute force, pixel by pixel. So they utilized a highly efficient algorithm for mean field inference. Mean field inference is a way of approximating the behavior of a massively complex graph. Instead of calculating the exact back and forth influence of every single pixel on every other pixel, it assumes that the nodes are somewhat independent and are just reacting to a mean field, an average background influence created by the rest of the image.
Like instead of asking 1,000,000 people in a stadium for their individual nuanced opinions on a play, you just listen to the roar of the crowd, the mean field, and update your individual expectation based on that macroscopic acoustic trend.
That's a great way to put it. And mathematically, because the pairwise penalties in the CRF were strictly defined by Gaussian kernels, the authors were able to recast this entire complex message-passing update as a high-dimensional filtering problem. By transforming the math into bilateral space, they could apply highly optimized algorithms to crunch the numbers.
And the inference speed result of that math trick.
Astonishing speed.
Yeah.
Running mean field inference for this fully connected CRF on a 1,000,000-pixel image required only about 0.5 seconds on a standard, off-the-shelf CPU, not even a GPU. A CPU.
Wow. Half a second to optimize a trillion-edge graph and perfectly snap the semantic boundaries to the physical edges. When you put these three massive methodological pieces together, the Atrous Convolution maintaining the 8x resolution, the ASPP branches capturing multiple scales, and the fully connected CRF snapping the final output to the raw RGB edges, the system becomes an absolute juggernaut.
Oh, undeniably.
Let's look at the experimental results that proved it, and the benchmarks and triumphs they achieved.
The proving ground at the time was the Pascal VOC 2012 semantic segmentation benchmark. This was the gold standard dataset everyone in the community was fighting over.
And for context, Pascal VOC isn't just a handful of clean images. It consists of thousands of highly complex photographs containing 20 specific foreground object classes. Things like aeroplanes, bicycles, birds, boats, dining tables, people, along with one massive background class. The images are wildly varied, objects are heavily occluded, the lighting is terrible, the scales are all over the place. It was designed to break algorithms.
And the metric used to judge success on Pascal VOC is incredibly strict. They don't use simple pixel accuracy. They use mean intersection over union, or MIOU.
We should define exactly why MIOU is so strict, because standard pixel accuracy is basically a vanity metric in segmentation, isn't it?
It is completely misleading. I mean, imagine an image that is 95% blue sky and 5% an airplane flying in the corner. If you write a terrible hard-coded algorithm that simply guesses sky for every single pixel in every image, it will be 95% accurate on that specific photograph. But it is a useless model because it entirely failed to find the airplane.
Right. It yields massive false negatives for the foreground object.
Intersection over union fixes this. For a given class, it takes the physical area where the model's prediction perfectly overlaps with the ground truth human annotation, the intersection. It then divides that area by the total combined area of both the prediction and the ground truth, the union.
Which means it severely punishes false positives where the model colored outside the lines, and it severely punishes false negatives where the model missed parts of the object. You only get a high score if your prediction maps perfectly to the physical reality of the object.
And on this brutally strict MIOU metric, the DeepLab system achieved a record-setting 79.7%.
Nearly 80%. That's wild.
It was a monumental leap forward over the previous state-of-the-art models that were hovering in the low 70s or high 60s. It proved that their decoupled, computationally efficient pipeline was vastly superior to the memory-heavy deconvolutional networks.
But they didn't just win Pascal VOC and stop there. They threw their architecture at several other grueling datasets to prove its robust adaptability.
Yeah, they evaluated it on Pascal context. This data set requires the model to densely label the entire scene, not just discrete objects. It has to identify stuff classes like sky, water, ground, and wall. DeepLab dominated it. They also tested it on the cityscapes dataset, which consists of ultra-high-quality street scenes recorded from cars driving through 50 different cities.
Cityscapes is the absolute bedrock for autonomous vehicle training. In that dataset, pixel-perfect segmentation of a pedestrian stepping off a curb or the exact boundary of a bicycle lane is quite literally a matter of life and death. DeepLab advanced the state-of-the-art there as well. But the dataset experiment that I found most fascinating was Pascal person part.
Ah, yes. That is a deeply complex challenge.
In standard Pascal, the network just has to label a human as person. But in Pascal person part, the network has to segment the human body into discrete anatomical regions. The head, the torso, the limbs, eyes even. This requires a level of spatial understanding that borders on true comprehension. Segmenting a lower leg is incredibly hard because the RGB texture changes wildly. One person is wearing blue jeans, another is wearing bare skin, another has dark trousers. The visual texture gives you almost no clues. The network has to rely entirely on the spatial relationships to make the classification.
And because DeepLab utilized those large field-of-view Atrous convolutions, it could see the entire human body at once, process the spatial relationships, and accurately segment the parts with remarkable precision.
The paper also serves as a fascinating chronological record of how the authors evolved the architecture over time. They didn't just build one model, they started their experiments by building DeepLab on top of the VGG16 architecture, which was the standard at the time.
Yes. In the VGG16 phase, they spent a significant amount of time exploring field of view sizes. They tested various Atrous sampling rates and kernel sizes, and they made a really interesting discovery. They found that using a standard, dense 7x7 filter yielded okay results, but the parameter count was massive. What worked best was using a much smaller 3x3 kernel, but pushing the Atrous rate way up to 12.
Spreading those 9 weights far apart.
Exactly. This specific configuration struck the absolute optimal balance of speed and accuracy. It slashed the number of parameters in the network from 134.3 million in their dense baseline down to just 20.5 million. It made the network significantly faster to train and run while simultaneously achieving higher accuracy because the broader field of view captured better context.
Doing vastly more with vastly less. But VGG16 eventually became outdated, so they swapped out the engine. They upgraded the backbone from VGG16 to the much deeper ResNet 101 architecture. And this is where we get to one of the most surprising analytical findings in the entire paper.
Yeah.
The trimap analysis.
Oh, this was a beautiful piece of diagnostic evaluation.
A trimap analysis is the ultimate stress test for boundary recovery. Explain what a trimap is for us.
Instead of evaluating the MIOU over the entire bulky area of the object, you isolate a tiny, narrow band of pixels evaluated right along the object's boundary. You ignore the easy pixels in the center of the cow, and you focus a microscope entirely on the transitional edge between the cow and the grass.
Does the model know exactly where the object ends?
Right. So they ran this trimap analysis comparing the output of the old VGG16-based DeepLab to the new ResNet 101-based DeepLab, and the results were shocking.
They found that the raw output of ResNet 101, before they even applied the fully connected CRF to snap the edges, had almost the exact same boundary accuracy as the VGG16 model after the CRF was applied.
Let that sink in. The neural network alone natively achieved the edge precision that previously required an entirely separate statistical mechanics algorithm.
How is that structurally possible? If ResNet is also doing downsampling, shouldn't it blur the edges just as badly as VGG?
The authors hypothesized that this native sharpness is due to the identity mapping inherent in ResNet's residual blocks. In VGG, data passes sequentially through every layer, being processed and smoothed at every step. But ResNet uses skip connections.
It's a fast pass lane for high-frequency spatial data.
Exactly. These identity mappings act almost like hypercolumn features. They preserve the sharp, local spatial fidelity deep into the network. Of course, when the authors finally applied the fully connected CRF to the ResNet 101 output, the performance leaped even further ahead, securing that massive benchmark score. But it proved how intimately the base architecture dictates the final spatial resolution.
Before we move off the methodology and results, I want to briefly mention a tiny, easily overlooked mathematical tweak they made to their training process that yielded massive outsized results.
They changed their learning rate policy.
The shift from the step policy to the poly policy, right? Instead of taking large jumps and abruptly cutting the learning rate, the step policy, they used a polynomial decay curve that smoothly shrinks the learning rate over time. And that single, seemingly minor change yielded a massive 3.63% absolute improvement in their validation score.
Which is astronomical in benchmark chasing.
It really is. Taking a step back from the hyper-specific mechanics, we need to look at the legacy and lasting influence of this paper, the ripple effect. Because DeepLab fundamentally altered the trajectory of the entire computer vision field.
It triggered a massive shift. For a substantial period, the combination of Atrous Convolution and fully connected CRFs became the absolute undisputed gold standard for dense prediction tasks.
But the research community didn't stagnate. They looked at the DeepLab pipeline and immediately started iterating on its blind spots. Trace the lineage forward for us based on the text.
Well, the immediate critique was the decoupled training stages. In this iteration of DeepLab, training is a two-step process. You train the DCNN, then you stop, and then you apply the CRF as a separate post-processing step. The DCNN has no idea the CRF exists.
So researchers began pursuing joint end-to-end learning.
Yes. They started unrolling the CRF mean field inference steps into the feed-forward network itself.
Swallowing the statistical model entirely into the deep learning framework.
Exactly. And what about Atrous Convolution? It spread far beyond segmentation. It became a core structural component in advanced object detection frameworks, specifically single-shot models like SSD and region-based fully convolutional networks, or RFCN. It was heavily integrated into visual question answering systems and even optical flow.
The ability to mathematically stretch a filter without adding computational weight was universally valuable. But what about the limitations? What did the paper acknowledge?
They acknowledged heavy computation for multi-scale inputs, even with ASPP. But the most significant limitation, which led later researchers to pursue weaker supervision, was the absolute reliance on dense pixel-level annotations.
You needed data sets where humans painstakingly traced every pixel. The cost of that is astronomical.
Right. So the quest for weak supervision using just bounding boxes or image tags was born from this bottleneck.
Okay, we have reached my absolute favorite part of the deep dive. It is time for the Novel Notions segment.
The extrapolation zone. I'm ready.
As a quick reminder to our listeners, this segment is strictly for entertainment purposes only. We are not predicting the future of the industry. We are just pitching one or two outlandish but plausible new research ideas inspired by the legacy of the DeepLab paper. We're creatively connecting its mechanics to modern research trends.
Let's hear the pitches.
Idea number 1. Temporal Atrous CRFs for video synthesis and deepfake detection.
Okay, applying spatial mechanics temporally. Walk me through the mechanism.
What if we take the spatial algorithm Atrous, the holes in the filter and the fully connected CRF, and apply them temporally across the z-axis of video frames? Instead of spacing out pixels to enlarge a 2D field of view, we space out frames analyzing frame 1, 5, 9, 13 to geometrically enlarge the model's temporal field of view.
Okay, so it captures long-range temporal context without drowning the GPU.
Yes. And here's where we apply the CRF. A fully connected temporal CRF would map the RGB values not just to neighboring pixels in 2D space, but to the historical pixel trajectory over time.
Because deepfakes often suffer from micro-flickering at boundaries because standard models lose temporal coherence.
Exactly. The spatial boundaries jitter. A temporal Atrous CRF would enforce strict mathematical consistency on edge pixels over time. It could either create flawlessly smooth video synthesis or, conversely, act as the ultimate deepfake detector by spotting temporal boundary anomalies.
It acts as a mathematically grounded lie detector for synthetic video. I like it. What is your second idea?
Idea number 2, a temporal attention for infinite context LMs.
Applying the holy convolution concept to large language models?
Yes. To solve the context window bottleneck, standard self-attention compares every single token to every other token, right? It's an n-squared computational complexity. What if we apply Atrous Spatial Pyramid Pooling ASPP to text tokens?
So instead of dense attention, you structure the attention heads exactly like the parallel spatial branches in DeepLab.
Precisely. Branch 1 looks at every adjacent word, rate of 1. Branch 2 looks at every fifth word, rate of 5. Branch 3 looks at every 20th word.
The elegance of that is the LLM maintains a massive field of view over an entire 100,000-word book without the exponential computational cost.
Exactly. And we snap to semantic boundaries like chapters or scene changes using a text-based CRF.
A fully connected semantic CRF over sparse attention, it is an extreme extrapolation, but the underlying mechanism is logically sound.
I absolutely love when theories map out across domains like that. This has been an incredibly dense exploration. DeepLab showed us that sometimes the best way to see the big picture isn't to step back, but to strategically look through the holes in the data.
Very true.
And as we move into an era of 3D spatial computing and augmented reality, how will these exact principles, spacing out our digital nets and snapping to physical RGB boundaries, dictate how our headsets map the physical rooms we live in? That's a provocative thought to explore on your own.
Absolutely.
Thank you for joining us on Talk Tensors. Keep diving deep.